Hello. I picked up one of these STM32 development boards on Banggood a while ago, about 6 months ago actually, back in December I think it was. And I've just a couple of days ago finally figured out how to upload a program onto it. So I've been looking at the blink program, the LED turning off and on yesterday, and I was very happy with myself to finally get to that point. So the reason it took me so long to get to that point is partially because the documentation is a little bit more scarce for this than it is for the Arduino stuff. And also I had a bit of a misunderstanding about how the loading of programs onto this works. So this is not going to be a tutorial as such, although it kind of is going to look like one, I suppose. But let me just say at the beginning that everything I'm going to show you in this video is the entire collection of my knowledge at this point as to how this stuff works. So if you want to ask questions about anything else in the comments, by all means go ahead, but don't expect any useful answers, because this is really the first step for me as well at this point. This is all I know. The other thing is it's going to be a fairly Linux-centric video. You can of course do all this stuff on Windows as well, but I haven't done it, so I don't know how to do it, so I can't tell you about it. So what is this? It's a 32-bit STM32 F1 chip. They seem to be commonly called F1, F3 and F4 and so on. And you can see on there, maybe, whoops. Oh, come on, focus. It is a F103C8T6. And the reason why this was interesting to me, if we just have a look at this other little board over here. Over here, this is a CC3D flight controller, and if this is going to kindly focus for us, we will see exactly the same chip on here. Come on, it always seems to be super slow focusing when I come to do the real video. Okay, just fuck that. Get out of here. Alright, just trust me, it says the same thing on there. And this board here is a STM32. Oh, come on, what is wrong with this? Ah, there we go. You just have to coax it into it slowly. So we can see on there it also says STM32 F103C8T6, exactly the same chip. Oh, my mistake. Sorry, this is not a STM32. This is just a 32. Although there is a rather suspicious empty patch to the left of that 32, isn't there? I wonder if there was ever anything else on this silk screen. Never mind. So anyway, this chip here is what is running a lot of the 32-bit flight controllers out there. So theoretically, you could use this development board and put some sensors on here, gyro and accelerometer and stuff. And of course an NRF24 L01 module, and fly a quadcopter with it. Hopefully that's, I don't know if I'll ever bother doing that, but theoretically it should be possible. So let's just have a look at where this came from and how much it is, because that's kind of a nice thing as well. It's only about $5 or $6. You get 3 of them for, yeah, $17 or so. And it has this chip, as we just looked at. Doesn't actually say a whole lot about the capabilities of it on here. So we'll have a look at we'll have a look at it right now actually. So if you Google that chip name, you'll find this page here on ST's website. And we'll have a look at this datasheet in a minute too, so that's where the datasheet comes from if you want to find that. And there's a little bit of info about it here, but it gives you quite a few advantages over the typical Arduino 8-bit AVR 16 MHz chip. Most notably is the speed increase. It's about 4.5 times faster than the Arduino CPU. You get twice the flash memory to load your programs into. So in this case, the chip that we have here is the 64 kilobytes of flash memory version. You get 20 kilobytes of system RAM instead of 2 kilobytes, is it? 20 kilobytes instead of 2. I think think it's only 2 kilobytes of RAM on the Arduinos. Anyway, so there's an improvement in all areas there, but most significantly in the speed, because this is going to let you deal with 32-bit numbers natively instead of having to do longer multiple calculations to deal with 32-bit numbers, as the Arduinos have to do. And then if we go down here a little bit more, there's a whole lot of other stuff as well, but stuff that we might be interested in is there are 2 I2C interfaces, 3 UARTs, and 2 SPIs. One thing that I did find out though is that this particular board, which uses the 48-pin package, doesn't necessarily expose all of these connections for us to use. It does expose the 2 SPIs though, so that's something that's good. So to get started with this, I noticed one of these comments down here, and this guy says great open source support, which piqued my interest. And then he says libopencm3 plus GNU ARM toolchain, shitty Eclipse, and OpenOCD, whatever that is. So I didn't use that, but this libopencm3 I did use, so that's what I'm going to look at in this video. And the GNU ARM toolchain, I actually already had this because I downloaded this to build my own versions of CleanFlight. So we'll look at getting that installed on your Linux box and this one as well. Alright, so just as a little bit of background as to why it took me so long to figure this out, I had this board that I bought in Japan just before I left. I was wandering through an electronics shop, and this was $15, and I'd sort of been thinking about getting started with some STM32 development, and this was billed as an educational package and easy to get started with and stuff. So I bought this and I gave it a try, and I managed to get this working with the libopencm3 fairly quickly, and I did that by using the USB plug here. So you just plug a USB straight into your computer, and on Linux it recognizes that. And if you go to this link here, you'll find, if you buy one of these, you can just plug it straight into your computer, and you can actually use the web browser. There's a browser-based compiler that you can use, and so you don't actually have to buy their proprietary compiler. You can basically, you edit your code in the web browser, and then you click compile, and it will send your code to them, and they compile it, and then they'll send you the binary. So you don't actually have a compiler, which didn't really seem like the kind of thing I wanted to do. I would rather have everything under my control. So that's why I used libopencm3 to do this, and it worked pretty easily. So then I bought this, and I thought this was going to be easy too, and I tried once again just plugging the USB cable in here as you do with an Arduino Nano, and basically tried the same stuff that I did with this board, and it just wasn't having any of it. So to make a long story short, I threw this in one of my boxes full of junk and just left it sitting there in misery for a few months until I decided to, actually I bought another one because I thought maybe that was faulty, and they both did the same thing. But anyway, supposed to be making a long story short. To make a long story short, you need one of these. You cannot upload your program through the USB plug directly. So I got one of these. Fortunately, they are not too expensive, $3.85. So you're looking at about $10 or so, or less than $10 so far. No, not less than $10, but close to $10. And basically, this is similar to the FTDI adapter, I think, that you use for uploading programs onto an Arduino Pro Mini and the like. So you just plug this end into your computer and put some wires between this and some pins on this thingy, and away you go. But again, there's a little bit more to it, which is why I thought I'd make this video. This video is basically just going to cover what I would have really liked to have known a few months ago. So like I say, it's not to be taken as any expert tuition, but more as just something that may hopefully save somebody some time in the future. Okay, so this is the PDF, but what I wanted to look at next was this page. So I'll put a link to this in the description below. And this is quite handy when you want to know how to connect things up. He's using something a little bit different. Is it different? I don't know. Maybe inside the one I have is like that. I'm not sure. But anyway, this is the one that I have, and the one that was on Banggood. So you can see he's connecting stuff up like that. So I basically just copied exactly what he has here, and so I'm going to plug this in like there in a minute. Blue, yellow, green, yeah. And keeping in mind this very important warning here. When developing and powering the STM target board from the programmer, so if you are powering it using this, so the programmer, we'll look at it in a bit more detail in a second, but one of these pins here is 3.3 volts, and he has this on the orange wire here, and he's left it unconnected there, so he's not using that to power the board. So he should be safe to plug his USB in there. But what I'm going to do is I'm going to use this orange wire to power the board, so I'm actually going to connect it. And in that case, you cannot plug the USB in at the same time, because apparently you may see some magic smoke. I did not feel like confirming that, so I'll just take his word for it and I'll stay safe. And anyway, these are the 3 connections you need to make. So I'll be making those connections, and I'll also be connecting the 3.3 volts to power it as well. So let's do that. Here's my... Oh, this doesn't stretch out very well. Okay. So this is... Now, why does this focus straight away? Look at that. So this is the ST-Link programming thingy, and I have my 4 pins plugged in there exactly the same as he did. So when you buy this, they kindly give you this little piece of wire with the 4 connections that you need to connect it up. So you'll have, if you buy the 2 things I showed you on Banggood, you'll have all this here ready to go. Oh, and the pins, I just wanted to... Okay, so he's saying PA13, PA14. These are, of course, references to the port numbers, or port B, so that'll be port A13 would be this one here. But that's not very helpful if you are looking at something like this, because you'll want to know where it is on this stuff here. And this is labeled as JTAG at the bottom there. So if you Google for this one here, I just Googled ST-Link JTAG pinout, and you'll find some stuff like this. I went with this one here, and I checked with my multimeter because they are a little bit different. So if you notice this one at the top, it's like I can't put my mouse on it because it puts this display underneath, but just you can see it goes ground, ground, key, something, something, something. So they're not all ground along that side on that layout. But when I use my multimeter to check what the pins are like on this one that I have, pins 20 up the side here through to 4 are all grounded. So this JTAG is, well, this is all the same as well, isn't it? I'm not sure, maybe these are just different names. Well, anyway, so all of these pins along the side here, that is the back edge, except for the very last one. So the bottom right corner is VCC. All the other ones along that edge are ground. So there's VCC there. And then the other 2 pins that we need are SWDIO and SW clock. Data IO, I guess that is. So those are the 2 pins just to the north of the center section. So that's those pins there and there. So I'm going to connect those up using that pinout. And so green is my ground that can go anywhere along that edge. Let's see. WDI. IO is blue, clock is yellow. So those are going to go like that and like that. And then VCC goes in the top right, and light should come on. In this other page that I showed you just a second ago, there is a link just above this warning. You'll see a link saying a few more related pictures can be found here. So I could hold this up to the camera and show you. Actually, no, I can't show you very well because it's all black. But you're probably better off just looking at his page and clicking on here and looking at the photos that he's taken, because they're very nice and clear to show you. Oops, I just clicked it. Oh. All right. Well, there are photos there. Just believe me. Whoops. Oh, is this them? All right. Now we're getting sidetracked, but there's some nice photos there. All right. So now that we have connected everything up, there are probably just another thing to point out is up on the top left, in this angle here, there are some jumpers. One of them says P2. You don't need to touch that as far as I know. And the other ones, if I could just shine a light there, they say boot 0 and boot 1. And I think you have to, actually I haven't confirmed this, I tried it before and it worked, but I think you have to move the boot 0 one across one position to the right when you upload the program. If it doesn't work when we come to do that, that'll be the reason. So I'll confirm that myself as I get to it. Right, back to this. Right, so if you Google for libopencm3, you'll probably come across this page fairly quickly. And there are two projects here, libopencm3 examples and libopencm3. And the examples uses the library itself. So that's the library itself. So I'm going to have an empty folder here, and I'm going to open up my Linux terminal, and I'm going to click on this one, the examples, and this will take you to the libopencm3 examples GitHub repository. And you don't actually need to download the library itself separately, because they have a nice little script that will get that for you from GitHub if you get the examples only. So I'm going to, of course, if you download this as a zip, you might have to get the, what am I doing here? Copy. All right. All right, so I'm going to do git clone, and then this is the examples repository. I don't think this is going to take very long. Okay, that's done. So if we have a look in here, we'll see there's a folder in here called libopencm3. So I think if you wanted to download the library itself separately, you could download it and just copy everything into this folder. But the way I'm going to do it is I'm going to use the script that they have prepared. And if you look at the usage info here, it says you must run make in the top level directory first. This builds the library and all the examples. So let's do that. This one. Just make this a little bit bigger. And shift this up, because otherwise it's going to go off the screen and you won't be able to see it. So make. Oh. Make. Right, this is really, really nicely set up. And I was very pleased to see how nicely it was set up, and impressed with the overall ease of use of it. And there was no surprise, actually, because when I looked at who was managing this project, wouldn't you know it, it turns out to be the same guy that's running the SIGROC project that I looked at a little while ago in that with that logic analyzer. So if we click on people here, look at this dude. again. So he obviously really knows his stuff when it comes to coding this. Oh, geez, look at him. He's all digital. Not surprising. Yeah, and he seems to be on the IRC chat forum pretty regularly as well, if you want to ask him questions, I guess. Actually, yeah, ask this guy questions, not me. And I might just follow him on Twitter while I'm at it, since I came here. Actually, just between you and me, I hardly ever go... I almost never look at Twitter, but it'll be nice for him to have another follower, won't it? Anyway, back to the story. So if we do make here, it tells us what to do. It's very friendly. So git sub module init. Actually, I don't think we run it in this folder. We have to cd into the libopencm3 folder and run that. And then we do update. So I'm just following the instructions here. And this is going to pull the libopencm3 library itself from GitHub for us. All right, and then I go back to the examples folder and do make again. And I'll just make that a little bit faster for us. It should be pretty fast anyway, because it's all just C, and C compiles nice and quickly. There we go. So that's it. Everything's built and ready to use. And if we go into examples, we will see STM32. And depending on what kind of board you are using, you'll have to... There are actually, unfortunately, different examples for each board type or chip type. But they do, at least both of the ones that I've used, they both have a blink sketch. So I shouldn't say sketch, should I? So the F4 one I used previously with this board here. This is actually quite a nice chip on here for $15. I thought it was pretty good. It's an F401RE. Lots and lots of memory, 168 megahertz CPU. Pretty good for $15, I thought. Oops, that's not right. This one. Anyway, but the chip that we're looking at right now is an F1. And there isn't... I don't think there's the exact same chip that we have on this board, but I found that this STM32H103, the examples in here, at least all the ones I've tried so far, are working with this particular development board. So there's a couple of them I'm going to look at in this video, and they are the Blink one, this one here, Mini Blink. And I think I might also look at UART printf as well, because it's very handy to be able to print something out as your program's running and have it tell you what it's doing. Otherwise you're just fumbling around in the dark blindly. So let's look at the Mini Blink, contents of the folder here, and we can see we have the source code file there, and then we have a program which is an ELF file. This is where it starts to get a bit foggy for me. I don't really know exactly what ELF is about. Let's just have a quick look at the source code. We may fiddle with this in a minute, but there we go. All right. So yeah, this is how I noticed the guy who's the maintainer. It's in the source code there. So this program is pretty simple, but you'll notice that it's not as simple as an Arduino Blink program. There's this funky stuff here, and this funky stuff here. You can see some parallels, I suppose, between the Arduino stuff, but it's a lot more verbose, isn't it? Because this is not really made for newbies. So I've come across some of this when I was dealing with the clean flat source code to do software SPI implementation for the NRF module. So I myself, I don't expect to be having too much difficulty with it, but it's definitely not in the same league as the Arduino sketch stuff, which is purposely made to be easy to get into. Anyway, so you'll see that this is a infinite loop which blinks the LED PC12, and there are 3 different ways you can do it. You can do it manually like that. This is setting the port registers using set and clear functions, or there is also a toggle function as well, which is the uncommented one at the moment. So this is the one that's just been compiled. So at this point, we also we need a means to use this thing, to talk to this thing, to upload onto here. So before we go any further, we'll need to find that as well. So again, unlike Arduino, there are quite a few things to get in place, but I think the rewards will be worth it. So to breeze through this as quick as I can, you'll need to get a utility called ST-Link, which will give you a program called ST-Flash, ST-Flash, which is the program that you'll actually be using to execute the upload. This ST-Link, I could not find this in the Fedora Yum repositories. So if you're using Fedora Linux like me, you're probably going to have to clone or download this and build it, which is what I'm just about to do. I think if you are using Ubuntu, you may be able to find this in the standard repositories. I'm not sure, but even if you can't, you'll still be able to build it like this. So I'm going to copy that, and then I'm going to go back to my terminal, whichever one it was, this one. No, it wasn't that one. This one. This one, okay. Just let me get my stuff in place. All right, so we are now here again, and we're going to do another git clone of that repository that we just copied, the ST-Link one. Every time I see this, I think it says stink. Cloning into stink. This is also quite small. He says, just before it slows down. Oh, come on. All right, let's just open this. Oh, it's not finished. All right, now it's finished. So in here you'll find an auto... No? Wait a minute, I thought there was autogen. Huh. That's a bit strange. No? Oh, it's just autogen, is it? I did this just before. Oh, I have to CD into that folder. I apologize. CD stink. Now we do autogen, and then we do configure, and then we do make, and that's it. So at this point you would, if you don't have this installed on, or if, obviously you don't have it installed, if you want to install it as a utility to use across your entire OS, you would change to the root user and do make install, or on Ubuntu you'd probably do it like that. So then that should give you the ability to, oops, it's ST-Flash is the actual program that is going to be flashing the program. So you should have this output when you type ST-Flash. All right. Oh, another thing I'm forgetting. Sorry, even before we even, getting a little bit backwards, but before we even try making the examples, we will need, if you go back to this one, we will need the ARM compiler. Right. No. So to get, jeez, probably the easiest way to get this, I really don't want to edit this video, so I'm going to do it all in one shot. Sorry for the delays, but I think if anyone's still watching at this point, they are determined enough to follow it through. All right. So if you go to my GitHub main page, you'll see my fork of CleanFlight there. If you click on that and go through to docs, development, and you'll see these things here: building. I made a contribution to this which didn't actually get accepted because it failed in a build, but I don't know why. Anyway, and then if you select the branch Fedora doc, you should see an extra file there which says building in Fedora. If you're on Ubuntu, you could look at the building in Ubuntu one, and this shows you how to set up the ARM toolchain to get the ARM compiler. I found that I actually tried my method, which is this one here. My method is building in Fedora. This actually works on Ubuntu as well. I tested it on Fedora 1820 and Ubuntu 14.04. And in my opinion, it's a little bit easier because you can do the whole thing with just those 3 lines in your command line. So you just need to get this tar archive, or this gz archive, tarred gzipped archive, and extract it. That's all you need to do. And then, of course, if you want to just be able to run the compiler from any position or any from any working directory, you'll also want to add it to your path. So this line here will add it to your path just for the current session. If you want to add it to your path for the future as well, you'll need to put this in your bash rc file, but probably if you know what a bash rc file is anyway, I don't need to be telling you what to do with this. So there'll be a bin folder inside that archive after you extract it. That's the one that you need to put into your path. So that once you have done that, you should have all of these ARM none EABI something utilities ready to use. So I should have actually showed you that before we downloaded and made the libopencm3 library. But anyway, we should be good to go now. So the part that I stumbled over, apart from not realizing that I needed that USB ST-Link thing to upload programs, even after I, or even while I was still using this one, one of my other stumbling blocks was figuring out the right sequence of commands to actually get the uploading to work. And this is where there is documentation out there, but I just found it really difficult to find for some reason. So, of course, once I found it, I forgot to make a bookmark of the pages that I found it on, although fortunately I did make a note of the commands that I need to run to get it to work. So make we just did before. This is my little cheat sheet here. So we need to do this ARM none EABI object copy, and then this will be the ELF file that we saw before will be the input. So that's going to be, if we go back into our examples, F1 blink, H13 blink, mini blink. So in this case it's called miniblink.elf, and we're going to make an output from that which is a bin. So it's just changing the format of that file to something that we can upload into this particular chip. And then we use this command stflash write blink bin, and then this, I think this is some sort of address within the chip memory that is the beginning address to start writing to. So yeah, this little bit here is a little bit foggy to me still exactly what's going on, but it works. So let's give that a shot. Let me just put that back over there. Get my All right, now we want to cd into the mini blink folder. So now we are in here, and we want to do make is already done, nothing to be done. Okay, so ARM none EABI I'm just copy this off here. Actually, no. I'll type it uppercase mini blink elf mini blink bin. No such file. Mini blink bin. What? Did I get that right? Uppercase O, right? Oh, binary. Ah, shit. For some reason, the Y keyboard on my keyboard is not working. The Y key on my keyboard, rather, is not working. All right, so that should give you no output. But if we look at our folder, we should now see a mini blink bin file, which is this is, I guess you would call this a hex for the typical Arduino stuff, or the like the clean flight builds. They're always a hex, I think. So this is that form that has been produced from this file here, which I think has all the debugging information in it as well. You can see it's a lot bigger. This is 111K versus less than 1 kilobyte for the actual final file. All right, so now that we have that, we can do st flash write mini blink bin to 0x800000. And this, I think this is not going to work. And this is where I should probably point out another thing that cost me about an hour of my time. When you may find that when you plug this stuff in while this is powered up, so this side is connected to the USB already, as I just did it before, you might see this light start flashing, and I thought to myself, oh, flashing is good. But no, flashing is bad. So if you see that flashing, you might want to just disconnect and reconnect it to stop the flashing. So I think it just sort of gets into some state that it shouldn't have gotten into when you were plugging in these wires one by one. Another thing you might want to just confirm is with LSUSB, you can see the devices that are currently connected to your USB bus. So I think for Fedora and Ubuntu, you shouldn't have to do anything to have the drivers for this available. So we can see it's here, ST Microelectronics, ST-Link V2. That should just be there automatically as soon as you plug it in. If it's not, I have no idea what to do, sorry. Probably for Windows, you'll have to install some driver to get that to run before you can just plug it in and have it work. Anyway, so now we have no light flashing on there. And like I said, at this point we may need to change one of these jumpers, because I read somewhere that the jumper should be in one position if you just want to run the program and in another position if you want to upload. So let's see what happens when we try and upload this. So this is ST flash. Did I shift this up? I hope I shifted that up. Oh. Permission denied. Okay, so in some ways I'm intentionally going through this in a way to show you where my problems turned out. So this one is easy. You just need to be the root user. So let's try that again. Flash written and verified. Jolly good. I say, jolly good. What? Jolly good, don't you know? There we go. So it says jolly good, and there's nothing really to look at. Okay, so now we should have a blink program running on there, but there's nothing to look at because that LED there is just a power LED. It doesn't show you anything more than the fact that there's power into the onto the board. So we're going to have to connect up an LED, and I actually just used my voltmeter for this to check it the first time, but since I'm making a video for people to look at, I set up a little LED like that we can check it with. And when I came to plug it in, I found, if we go back to this source code for this blink program that we are running, it says blink the LED PC12 on the board. And I kind of looked around here for where to plug my LED into, and then I noticed that there isn't actually any PC12 exposed to use. And this is just because this chip package type is the 48 pin one, and there's just not enough pins to expose all of the connections that it has. Where is it? This one. Yeah. So this is the LQFP 48 pinout with 48 pins, and you'll see that there is no PC12 on any of these pins anywhere. So it's not just a matter of this board not having broken them out correctly. This board, as far as I can tell, breaks out every pin that there is on this chip to use. It's just that this chip doesn't have them to use. If we scroll up to some of the other package types, we'll see there's a 64 pin out one, which probably does have a PC12 somewhere, I guess. And there's actually also a 100 pin out. So there's quite a lot of functionality in this chip that we are not necessarily going to be able to use. So when I looked at this page here and showed you that it's got, you know, this many I2C interfaces and so on, I haven't actually looked into how many we can actually use on this particular chip. Anyway, so what can we do about this? Well, I did notice that we had some other ports that had 12s on them, and it'd be great if it could just focus. So in the bottom right, you can see there are 2 ground pins on that last pair of pins, and then there's PA11 and PA12. So I decided to just use PA12 there instead of PC12. So if you go back to here, so unlike Arduino, this is where it gets a little bit more arduous. If I search for GPIO-C, we'll see that there's quite a few places that we need to change. It's not just a matter of changing one number to use a different pin. So we have to set up the ports on a different sort of a method. So I'm going to change that to A and that to A. And basically every uncommented occurrence of GPIO-C, I'll leave these ones there because they're commented. Every uncommented occurrence of GPIO-C I'm going to change to GPIO-A, and then the 12 will remain the 12 as it was before. So save this and then come back here and now I'm the root user, aren't I? So let's do make and then do this again. Mini blink elf, mini blink bin, and then flash again. Alright, that's flashed. So now it should be turning this pin PA12 high and low. Oh yeah, in case it wasn't obvious from this program, this loop here is just waiting a bit. So it's just turning the LED to whatever it was, changing it from what it was before and then waiting a while. So if we plug this in, making sure we get it around the right way, any one of these along here should be a ground. And then this one on the left, I think, is PA12. Alright, there we go. Yay! Quite a bit of work just to get that done, wasn't it? But you know, this is just a start. Come on. Oh, it's beautiful. Oh, look at it flashing. Oh, very exciting. So yeah, I'm not too sure what the timing would be here because, well, this is probably one cycle, one instruction cycle, one cycle, yeah, one clock cycle, and this would be at least 3 here, and then there's probably some more in there. So it's a little bit hard to say, a little bit hard to measure from this what speed the clock is really running at the moment. But anyway, so we have a flashing LED. The other thing I wanted to look at was getting some debug output on the UART connection, which is quite conveniently broken out over there on just above my thumb. You can see 5 volt TX RX ground. So again, if you wanted to power this from 5 volts, you'd probably have to unplug your 3.3 volt wire from there just to make sure you didn't ruin anything. So I'm going to load up the UART printf example, and I'm going to connect my Arduino. Actually, no, I'm not going to do that, but you can just take my word for it that in the default configuration we just get garbage printed out on the UART result if we look at it on the Arduino IDE. So let's go over to there. You start printf, and now we are in this folder. Where is it here? So now we are in this folder, and we're looking at this stuff here. So again, we want to do, well, make is already done. Actually, I am going to edit this file because, let's have a look at it first. Again, so we should be able to see from here that there's a lot more to getting what seems like quite simple stuff in Arduino, just to print out some stuff on the serial port. So all this is doing is it has these numbers here, and it's incrementing them in a loop, and then it's actually turning that pin off and on as well, and then it's printing out hello world, and then it's printing out those three numbers. Nothing really complicated. Oops. But you can see that it takes a lot more coding to get something quite simple done than it does in Arduino. So let's, did I change anything? No, I didn't change anything. All right, save. Oh, yeah, so what I wanted to change here was at the beginning you set up the baud rate for the UART connection. I want to change that to 9600 baud. So I'll save that. I just want to change it to something that my Arduino can handle. I think I will connect up the Arduino to check it. Right, so make. Oops. And then we do the obj copy, except this time it has to be usart print elf, usart print bin. And then the flash, we have to change that to usart print bin. And then when we run that, we should see our LED stop probably. So that took a little bit longer to write, didn't it? And also, surprisingly, look how big that program was, 26 kilobytes. That's really big, isn't it? I don't know why it needs to be that big just to do a little hello world output on the UART connection. A little bit strange, a little bit worrying actually, because there's only 64 kilobytes of memory space to use total. I don't know about that. Anyway, so now on this output pin here, the TX pin, we should have some hello world serial output being given. Okay, so let me just, how are we going to do this? Let's do it with an Arduino. Right, have an Arduino there. And I only need two wires here, so one's going to go to ground and the other one's going to go to TX. So black is ground, white is TX. This is another long video, isn't it? Do you like long videos? And then over here, one goes to ground, and one goes to RX, which is, if we look at the little arrow, oh, it's labeled as well, so RX is 0. Like that. Now if I open my Arduino IDE, and I open, oh, hang on a minute. Board is Arduino. Okay, so dev TTY ACM0 is the USB port that this Uno is connected to. And if we open the serial monitor, error opening serial port, why is that? Hold on a minute. try that again. I seem to get this sometimes. Alright, so for some reason I couldn't open that port as a non-root user, but we open it up and we are at the right baud rate, but what we see in here is sweet FA. Nothing. So I got a bit puzzled as to why nothing was coming out. So rather than looking at this with an Arduino, see, that's why I said I wasn't going to bother doing that, because it was rather pointless. But now you don't have to take my word for it. You can see it for yourself. Yeah, it's this here, isn't it? Stale lock file sometimes happens. I don't know why that happens really, but it's a bit of a pain in the butt. Right, so instead of using an Arduino, let's look at it, what that pin is doing with a logic analyzer. So again, we are going to connect up to ground and TX. I did get that right, didn't I? Yeah, ground and TX. Okay. So this should be digital channel 1 on there. And again, I have to be I have to be root again for this. ABC 1 2 3. And pulse view. Hopefully that works. Yes. And then run. All right. So if we take some samples of this with our logic analyzer, we will see that there is actually something coming out, just nothing that the Arduino could recognize as useful output. And this UART, analyzer, I think they call it something else in this program. No? Oh. All right, so put this onto channel 0, channel 0 at 9600 baud. Oh, wait a minute, it's working. HE. Hey, wait a minute. Oh, it is working. What's going on here? HELLO space WORLD. Big goody mark. Space. That's funny. What? Maybe, oh, okay, it works. Well, that sort of took the wind out of my sails, but maybe when I was doing this before, I played around with something else, because it didn't just work straight out of the box like that. No, do it again. HELLO world. Okay. Well, I don't really know what to say there, but I was expecting that we would see garbage output from that, and when you get invalid stuff coming out on the UART connection, you'll see a third row in here. At the moment, we can see only oh, there it is. So RX bits and warnings. So when I tried this the other day, RX warnings was just full of frame errors all the way along, and the data was not being received correctly at all. Actually, let me do. I want to see if I can do that again, because what I did there was I did this. I took this delay loop and I put it in there. So it's going to print out, at least this was my thinking, was that it was going to print out hello world like that. Then it was going to wait for that amount of time. As we saw before, this was the amount of time that the LED was flashing. So I save that and then build. Oh. Yeah, whatever. try this again. Build it and flash it. Right, now we go back here and try this again. Run. What? It's doing exactly what it should. That's weird. This is so weird. I don't know why it didn't work before, but this is exactly what I expect. Huh? Stolen my thunder for the second time in 3 minutes. So it's working perfectly. Hello world. And then there'll be some numbers, whatever the numbers are, after that. Okay, well that works great. Anyway, I was going to say that I had a problem and then I managed to figure out how to fix it. But the problem that I was having was that the timing of these ups and downs, essentially you can see where they're close together like that. That is basically 1 bit of data. And they were too slow for 9600 baud. And I measured the timing of them because you can put a timing, you can put one of these on here and see how fast they are. So you can see 104 microseconds. Yeah, that's. And when I did it the other day, there were 313 or approximately 312 microseconds. So for some reason, the pulses were a third of the speed that they should be. And I found that, of course, when I changed this from 9600 to 3200, all of a sudden all the messages were showing up correctly. They don't now because it's the wrong speed. But I thought I was quite smart for figuring that out. And then I noticed that one of these functions up here, right at the beginning, is what looks like a clock scaling function. So set up in HSC 8 megahertz, out 72 megahertz. So it's a factor of 9 scaling there. Anyway, I played around with this for a bit, and I found if you Google this function name, you will find not a whole lot of detailed documentation, but you'll find some other functions, and I think it was 25. When I did that, I found that my 9600 baud that I expected to work that wasn't working would work with 25 megahertz scaling. So I'm not really sure why it's working perfectly now, but I'm kind of happy that it is, and I guess it's better to show you that it works than that it doesn't work. So anyway, now we have a very nice way to say what the program is doing. So you can say, I screwed up. So now if you're wondering what the program's doing, you can use your, well, you probably wouldn't use a logic analyzer. Oh, maybe it did screw up this time. Oh, well that's weird. I wonder why it didn't show the first time. So there we go, I screwed up. Right, so I guess the question remains, why didn't the Arduino work? This video really should be finished by now. It's almost an hour long, but I'm kind of intrigued as to why the Arduino was not working just before. So let me just plug that in and give it another shot. Arduino, what's wrong with you? RX, right? RX, ground, and then on this side we have ground and TX, like that, right? Arduino IDE, ACM0, go. Arduino, what's wrong with you? Well, I don't know what's going on here. Oh, is it because this is running on 3.3 volts? Maybe that's what it is. But I was getting input. I don't know. I'm sort of losing the plot here, but this is running at 3.3 volts, right? So it could be just that the logic level is not quite high enough, but I don't think so. I'm pretty sure that this would accept a 3.3 volt signal on the UART connection, wouldn't it? Pretty sure it has in the past. Anyway, so when I connected this up the other day, and I looked at the Arduino serial monitor here, it was just pouring out screeds of garbage text because it was receiving the wrong speed input. All right, I think this is far more than enough needed to be said, and we're just on 1 hour. So yeah, that's it. Thanks for watching. Did anybody watch the whole thing? Let me know. All right, see you next time.